Hey everyone, welcome to the beginning of Unit 3. Today I'm actually not going to start Unit 3 right away. Rather, today we're going to be talking about some math skills, which is definitely everyone's favorite part. And these skills are going to be really important in this unit. This unit is all about energy, but it does involve a lot of math in some spaces, and we're going to kind of go through some important things to know so that you're not confused when we go into the actual concepts, and you'll be able to understand everything a little bit better. I'll also give a bit of a disclaimer. Some of these math concepts are quite advanced and are things that you're going to learn in higher level math courses, like in grade 11 math later on, and in grade 12 calculus and vectors or advanced functions. So I'm going to give you kind of the overview of them so that you don't need all of the background information and you can still use them effectively. So there's some things I might tell you to just kind of gloss over because you'll learn way more about them later on. Alright, there's a couple different things we're going to go through, but I'm going to start with a really simple one, and that is what is a scalar versus a vector. This is pretty much review. We've probably talked about this before, but I just want to highlight this difference because it's going to become important in the next section. So we know that a vector is something which has a direction and a magnitude. And what we mean by magnitude is just that it has a size. So like here's a vector, and this kind of distance is its magnitude, and it has a direction, which is like this angle or whatever you want to say. We've done this stuff. We know that a scalar is just a normal number, so it only has a magnitude, is one way to think about it. You have a size, but you haven't specified a direction. You might use a scalar to just be distance, and then if you give that distance a direction, it becomes displacement. We've learned all this. I just want to emphasize the difference between scalars and vectors because I'm going to be using the term scalar in the next section. Alright, the first math concept might be one you already know and might not be. And that is the concept of an absolute value. So what is an absolute value? Well, this is why the scalars and vectors come into play, because absolute values mean different things for scalars and vectors. So first of all, how do you write an absolute value? Well, that's really simple. If you have a number or a variable, you just put these two bars around it. It's like putting brackets around it, except the brackets are straight, so you just put bars. That's how you indicate an absolute value. That could be a scalar value, like a 23, or it could be a vector value, like 45 meters this direction. You might also see, obviously, the vector variables. So what do absolute values actually mean? Well, like I said, they mean different things for scalars and vectors. Scalar absolute values are just the positive value. So this is really simple. If you have an 8, the absolute value of 8 is 8. If you have a 2000, the absolute value of 2000 is 2000. But if you have a negative number, like negative 10, the absolute value is positive 10. Basically, you just make the number positive. If it's already positive, it stays positive. If it's negative, it becomes positive. That's how you take absolute values of scalars. Really easy. Absolute values of vectors are kind of related, but they're a little different. Vector absolute values are just the value which is just converted to a scalar, basically. Basically, you're just removing the direction information. So, the absolute value of 25 meters north is 25 meters. The direction information is gone. We no longer care about it. We just care about the magnitude. The absolute value of, whatever, let's say 30 meters south, 30 degrees north. Doesn't matter. It's just 30 meters. So that is how we calculate absolute values for scalars and vectors, and you'll see this notation with the two bars and the variable in between them quite a bit. Okay, the next thing we're going to talk about is kind of an interesting concept, and it is called a vector dot product, which is a very complicated sounding name for something that's not so complicated for what we're using it for. So basically this is the deal. We've been dealing with a lot of vectors up until now. Previous 2 units, we've done vectors a lot. But you'll notice that all we've ever really done with vectors is we've added them or we've subtracted them. At no point did we really go and we're like, we want to multiply or divide vectors, which we can do. Just like we can multiply 5 by 3, we can multiply vectors 5 meters north by 3 meters south. But what to do when you actually multiply vectors isn't super intuitive. Adding vectors is pretty intuitive. If you have a bunch of vectors, basically adding them just amounted to putting them end to end and seeing where you ended up, basically. And subtracting them could be similarly intuitive, you're just taking away that. But what do you do when you multiply vectors? Well, this is actually a very complicated concept, complicated enough that a good portion of grade 12 calculus and vectors is devoted to explaining what we do when we multiply vectors. But for our purpose, since we're going to need to be multiplying vectors, I'm just going to explain the really basic without really explaining the why behind it. Basically, when we multiply vectors, we can't just use the normal multiplication sign. We can't just say, vector A times vector B, because this multiplication sign conveys certain things about multiplication that are not necessarily true when we're multiplying vectors. So mathematicians are like, okay, we need to invent a new symbol. And the symbol that they came up with is literally a dot. Not a period at the bottom like this, but a dot in the middle like this. And this is why it's called a dot product, because the symbol that mathematicians decided to use for it is a dot. It's a product because when you multiply two numbers together, the thing you get is called a product, and you're using vectors, hence vector dot product. This dot product is, can be calculated in a variety of different ways, and we're going to use a relatively straightforward formula, which is not going to look straightforward immediately, but bear with me, which is basically that a dot product of B is equal to absolute A, absolute B, cos theta. And you're going to be like, what? What is this? I'll try and explain. But I will point out that this formula is important enough that you should really have it somewhere whenever you're writing tests, doing questions, etc. This is really critical. So what are these really doing? I'm going to kind of draw a diagram to help explain. Here's like a coordinate grid right here. And here's two really random vectors. Here's A and here's B. And we want to multiply them. So I'm going to label this A and this is B. These are two vectors. We want to multiply them. What are we going to do? Well, we're going to take the absolute values of both vectors. We just talked about absolute values. That just literally means taking the magnitude without the direction. So if this distance is 10 meters, we don't care about the direction. We're just going to be like, 10 meters. Good. Same here. If this is 14 meters, we're going to be like, don't care about the direction. It's just 14 meters. And these are all multiplied together. So this is a 10 and a 14. What is theta? Theta is this angle between the two vectors. Now, this is a little different. This is not the angle from the origin upward or anything like that. It's not that angle. It's the angle between the two vectors. And that is theta. And it's going to go here, but we're just calculating the cosine of it. And by calculating the cosine of theta, let's assume, theta's 15 degrees. When we multiply these three numbers together, we will get the dot product of vectors A and B. This is how you can calculate dot products in the simplest scenarios, and this is all we're going to be needing to do with dot products really in this unit for the most part. There's a little more, but we're going to talk about it later. For now, the important thing to remember is that this formula is how we do vector dot products. And it's pretty straightforward. Whenever you do the dot product of vector A dot vector B, it's the absolute value of vector A times the absolute value of vector B times cos of theta, where theta is the angle between the two vectors. Okay. Last topic we're going to cover is something kind of interesting, and that is graphing sine and cos. And graphing sine and cos. And I'm going to explain why this is important after I do it. So we've graphed a lot of things in high school. We've graphed linear equations where you have y equals mx plus b. We've graphed quadratics where you have y equals x squared plus 2x plus 3 or something like that. We've done a lot of different graphing, but there's a lot of equations which we have not graphed, which we definitely can. And what we're going to do today is graph these really simple things. Y equals sine of x and y equals cos of x. You might want to replace the x with a theta if it makes you happier because it is an angle. These two functions, or equations, whatever you want to call them, which you're going to learn so much more about later, are really important. Up until now, all we've really learned about sine and cos is that essentially they are just telling you about right-angled triangles. They're pointing out that if you're measuring an angle and you label the sides adjacent, opposite, and hypotenuse, that sine, the so part, is going to be opposite over adjacent, opposite over hypotenuse, and cosine of theta is going to be adjacent over hypotenuse. And this is theta. We know this about trig, we've learned this. But what we've never really done is said, oh, this gives us values. What if we plug these values in and literally just try and graph them? And that's what we're going to do now, and I'll show you why once we've done it. So I'm going to create a graph, and this is how it's going to work. One thing that you might not know about sine and cosine, but you're just going to have to kind of, again, take at face value, is that sine and cosine have values between -1 and +1. You cannot get a value of cosine or sine which is greater than +1 or less than -1. All the values are between these numbers. You can test this by literally plugging into your calculator and being like cos 10,000, which is like a huge number, and it'll still be about 0.17, still within this range of -1 to +1. So I'm going to construct a little graph here, and it's going to basically look like this. We're going to have a line here, we're going to have a line here. On the x coordinates, we're just going to have, at the top of this, we're going to have a +1, and at the bottom of this, we're going to have a -1, because that's really all we need here, because again, they can't go further. And on the on the x, I'm going to label degrees. This is going to be 0 degrees, this is going to be 90 degrees, this is going to be 180 degrees. I'm just going up in increments of 90 to 70 degrees, 360 degrees. And that's one full turn around a circle, like, 0 degrees all the way to 360. And so that's more than enough for what we need it for. And now we are going to graph sine and cosine the old-fashioned way, literally by plugging in specific values, which I'm just going to use the values I've labeled, and drawing them on the screen. So I'm going to use, blue is going to be sine, and red is going to be cosine. So let's start with sine. I'm physically entering this into a calculator, by the way, in case you're wondering where I'm pulling these numbers out of. Literally just entering sine of what I'm putting in. Sine of 0 degrees is 0. So literally 0 degrees is 0. Sine of 90 degrees is 1. So at 90 degrees, sine is 1. Sine of 180 degrees is 0 again. So, over there. Sine of 270 degrees is -1. So, it's going to go down about here. And finally, sine of 360. Sine of 360 is going to be 0 again. And you notice that creates this kind of zigzag. If you drew this just by connecting the lines, it would be this, which is not a good sign, but it's an explanation of that. Let's do cosine now. Okay, so the cosine of 0 is 1. So we're going to put a 1 right there. The cosine of 90 is 0. The cosine of 180 is -1. So I'm going to put it down here. The cosine of 270 is 0. The cosine of 360 is 1. It's going to go right there. You notice this creates a different sort of zigzag from the previous one. It's still a zigzag. If you went before this, it would actually be the same zigzag, because if you extend these, this would go back down here and back down here, just like these would go, and it would all be the same zigzag, but kind of in a different position. Now, one thing you wouldn't know, but I'm going to kind of just tell you one of these things, is that these are not straight lines. You can probably assume that. And if you actually graphed all these intermediate values, which, not that I recommend you actually go through and do that, you would realize that it makes this kind of very specific curve, which I'm going to do a terrible drawing of right now, where it basically does something like this, and it goes down like this, and back up like this. This is not a good drawing, but it will do. Cosine does something kind of similar, where it goes like this, and down like this, and back like this, and up like that. No one thinks these are amazing lines, but they'll illustrate the point. You'll notice something about these lines if you look at them, and that is it's literally the same line, but they start at different points. Because if you continued this line, it would just be going down again on both sides. And so you could predict basically that you notice how these are basically the same thing, but this starts here, whereas this starts here. There's this offset. Cosine is literally behind sine by a certain amount, and that amount is 90 degrees. You notice that? If cosine reaches 90 degrees and it's 0, then at 180 degrees, sine reaches 0. It's exactly 90 degrees off. But they're the same exact graph. Okay, the important thing to take out of this graph, besides the fact that sine and cosine make these fancy waves, which are called sine waves and cosine waves, is basically these important values. And that is the values at 0, at 90, at 180, at 270, at 360, for both sine and cosine. These values, you'll notice, are pretty predictable. You start at 0 and 1, and then it goes basically up and down, following the same pattern to +1, -1, 0, +1, -1, 0, and it's always those numbers, and it just kind of goes up and down. And if you went beyond 360 degrees, this pattern just repeats again, like you're just going to end up back at the start again. And this is kind of the magic of sine and cosine. They repeat over and over, which is why the values are always between +1 and -1. For your purposes, I would draw a graph kind of like this into an organizer or a sticky note or something, so that you have these values ready, so that you know at a moment's glance that, sine of 0 is going to get you 0, but cosine of 0 is going to get you 1. And yeah, you can always plug those into a calculator, basically what I did, but it's good to start to internalize them because they're going to come up a lot in our next topic, which is work, where we're going to use some of this trig to do more complicated kind of calculations, and this stuff is important. Okay, so just an overview of what we've really discussed today. We started off talking about scalars versus vectors. Scalars have magnitude, vectors have direction and magnitude. We looked at how to calculate absolute values. For scalars, just removing the negative. For vectors, ignoring the direction. Then we looked at vector dot products, and we remember this important formula: absolute value of vector A times absolute value of vector B times cosine of theta, where theta is the angle between the two vectors. And then finally, we graphed sine and cosine on this little graph here so that we could learn about these special values where sine and cosine are whole numbers. At 0, at 90, at 180, at 270, at 360, sine and cosine are whole numbers. And nowhere else. Everywhere else, there's very specific fractions that you can throw into a calculator, but these are the special values where sine and cosine are whole. So that's about it for today. Hopefully these math skills came in handy for understanding both the lesson we're going to do a video on next time, and also just this unit in general. In the next video, as I said, we are going to talk about work and all about what that is, and how we're going to use all of the stuff I just showed you today to calculate it. I promise it's not as confusing as it sounds. That's about it for today. Thanks for watching, and I'll see you next time.